So hello everyone and welcome to the next talk. The next talk is on galaxy morphology by Professor Hasan. And yeah, so over to him. You were introduced earlier, no? Sure.
Yeah. Hello everyone. So welcome to our next second session. I'll be speaking to you on morphology of galaxies, and then we would given a chance look at how we can study that using certain software which is available. So essentially I'll go through the basics because there are many in the audience who are new to astronomy. So I'll rush through a few important concepts which will link you through all the other course lectures too. So if you are lucky to be living in a place where you have a very clear and dark sky, you will see a band in the sky, which you see here. And this is the Milky Way, right? For a long time, people didn't know what it was. They thought it was fluid flowing there. And hence it was called the Milky Way. In fact, even in India, it was thought it was a river in the skies, and it was called Akash Ganga, the Ganges river of the sky. Later, when Galileo turned his telescopes towards this patch, he realized that it was not fluid flowing, but it was comprised of innumerable stars, many stars, and the light, it looked nebulous because of there were so many of them, and because of scattering and so on. So what are galaxies? Galaxies are large collections of stars, gas and dust. And when I say large, I mean billion stars or 100 billion stars, right? If there are groups of stars which are in hundreds, thousands, or even millions, we do not call it a galaxy. When the collection go up to billion, 10 to the power of 9 or 100 billion, then we call it a galaxy. So apart from stars, it has gas and dust. Gas is the raw material from which stars are formed, and dust has material. If it enriches the gas and star formation takes place, then there are chances of planetary systems evolving. So typical masses of galaxies are about 10 to the power of 9 to 10 to the power of 12 solar masses. And mass of the sun, as we know, is 2 into 10 to the power of 30 kilograms. Typical sizes of galaxies are about 100,000 light years, which means the time taken for light to go from one edge of the galaxy to the other takes 100,000 years. And as we all know, light travels at a phenomenal speed of 300,000 kilometers per second. So a pulse starting from one end, traveling at the speed of 300,000 kilometers per second, if it travels for 100,000 years, then that's the distance of a typical galaxy. And there could be galaxies which are larger than this or slightly smaller than this. Since the scales get too big in astronomy, therefore people use different units of measurement. You have the light years, you have AU, astronomical unit, when you are measuring things at the level of a planetary system. 1 AU is the distance between Sun and Earth. And then when you are measuring the solar system, you talk in terms of AU. When you are measuring distances between stars, you go into light years. And then there is another scale called the parsec. So 1 parsec is 3.26 light years, and kpc is kiloparsecs, which is 1,000 pcs, and so on. So in terms of kiloparsecs, our galaxy is about 30 kpc, right? So 1 kpc is about 100 parsecs. So you have a beautiful picture of the sky here from a very clear from a region where the skies are extremely clear. And this is the band. This is a beautiful Milky Way. And we are sitting inside it and picturing it from within. The first map was given by Herschel. And this is Herschel's map of our Milky Way. He thought the sun was at the center, and this was the galaxy. The beautiful part of this is Herschel did get a flat structure. He did see that our galaxy was some kind of a pancake, but he made a few mistakes, and the mistakes were because that's what the astronomers thought. Herschel thought that all stars have the same magnitude, which means all stars have the same brightness. Magnitude is another term used to indicate brightness. So all people earlier thought all stars are equally bright, and if a star appears fainter, then the object is very far from us, and if it is brighter, then the star is closer to us. So Herschel, he looked at the skies, and the stars which looked faint, he marked it closer, and those which were far, he marked it further. So that was the mistake. The first mistake was all stars have equal brightness, and today we realize it is not so. Some stars are more massive, hence they are hotter and they are brighter, while some are less massive and hence they are colder. So the temperature range can go from 3,000, 3,500 to 40,000 Kelvin. Second mistake which was there at the time was they did not realize that there is medium between stars, that there was something called interstellar medium. So the experience was, as you move away from Earth's surface and you go further and further up, the atmosphere becomes thinner, and finally fades into space, and there is nothing there. So people thought that there is no medium between stars, but it is not so. There are regions in space where there is a diffuse medium. Even if it is diffused, the distances are so large that they finally add up a lot. And if you are seeing a star through this medium, interstellar medium, then as the starlight passes through it, it gets scattered and get absorbed, and the star looks fainter. It's something very obvious. If you see a car approaching you and there is a cloud dust in between, the car light would look faint, right? So this is what happens. But at that time, they didn't know that there was there's medium in between. So using this, he made a plot. And third thing was the instruments, the telescopes and techniques were different. So Herschel actually was observing the map which you see on the right hand side. Today's understanding of our visible extent of our Milky Way is this green dashed line, and Herschel has mapped only this amount because he could not see through the center, there's a lot of obscuration because of a lot of material being there, a lot of dust and gas being there, and there were limits to how good the telescopes were, and hence he thought the sun was at the center. Just a slide on the history of galactic astronomy. The reason I am giving it is to tell you that our understanding of what galaxies are is pretty recent. So in 1610, when Galileo turned his telescopes to the Milky Way, he realized that it was made up of stars, right? It was in 1610. 1750, Immanuel Kant, German philosopher, he theorized and said that other nebulous objects, things which looked fuzzy and nebulous, they were galaxies by themselves. But it was just on philosophical grounds. He said, like you have a solar system and you have stars, they mesh, right? So, but this was not scientifically accepted or proved. And in 1774 to 1791, a person called Messier, who was interested in looking at comets, he made a catalog of objects which were fuzzy but were not really comets. Actually, those were the objects which were disturbing his interest, and he made a catalog of these fuzzy objects which fuzzy are nebulous objects, which are not clearly point-like like a star. And this Messier catalog later proved to be a collection of a lot of galaxies and globular clusters. And then we have William Herschel and his sister Caroline Herschel, brother and sister pair. They did tremendous amount of observing, and very meticulously they surveyed the skies, and they catalogued uh, 5,000 nebulae. Yeah, and they could also resolve some individual stars in some of these nebulae. Shapley in 1918, he said that that Herschel's model of sun being at the center of a galaxy is not right. He looked at globular clusters. Globular clusters are clusters of stars. There are thousands or millions of them in bunches, and they're distributed around. He saw the distribution of these globular clusters. These globular clusters, they themselves are arranged in a spherical distribution, and the center is not where the sun is. And Shapley said that sun is not at the center of our Milky Way. The center is somewhere else, because these globular clusters are not centering the sun but some other point, right? So human ego kept shifting. There were times when people thought Earth was the center of universe. Then they said, no, sun is the center of our solar system. We are third there. And then we realized, we said, okay, fine. Our sun is the center of the whole universe, and the whole universe is the Milky Way galaxy. And even that got taken away from us, that we are not in the center of our Milky Way. And in 1920s, there was a debate between the same Shapley and Curtis, where Shapley said that the whole universe was just one galaxy, which is our Milky Way galaxy. And Curtis said that there are many more galaxies other than our Milky Way, right? And this debate was resolved in 1920s by observations of Hubble and Emerson, where they could estimate, they could, one thing, resolve stars in Andromeda galaxy, Andromeda Nebula, that's what it was called at the time. They could resolve these objects in a more better way than Herschel and all did. And other than that, they could find certain variable stars called the Cepheid variables. And the Cepheid variables are variable stars which pulsate. They become bright, they become faint, and there is a relationship between the actual luminosity and the period. So there's a period luminosity relationship. Using that, they are being used even to this day to find distances in astronomy. So using some of these Cepheid variables, Hubble and Emerson showed that Andromeda Nebula was much, much beyond the extent of our Milky Way, establishing that Curtis is right. There are other galaxies than only our Milky Way. So this brings us to, so in 1920s, just 102 years from now, people thought Milky Way was the only galaxy, right? So it's a recent field, and much has happened in the last 30, 40 years. So a lot of work in galaxies and understanding galaxies has happened pretty recently. So how do we understand our Milky Way today? We understand it, if you look at it face on, then it looks like a spiral galaxy. And in fact, it's a spiral galaxy with a bar. If you look at it edge on, then it looks like a slice, right? So this is what we are seeing here. We are sitting inside it and trying to map the stars. So this is how it looks. But if we could, or somebody could, or if there are people beyond, they are in Andromeda galaxy and look down on our galaxy, then they will see our galaxy look something like that. Okay. So yeah, this is the edge-on view, and this is the face-on view. There are three basic components. One is the disk, one is the bulge, and the halo. Right. So we break up our galaxy in three basic components. the bulge, the disk, and the halo. The globular clusters are found in the halo. You don't see much gas and dust there. The bulge has a lot of stars, old stars, young stars, small stars, dead stars, and so on. And you don't see many young stars here. At least that's what a earlier picture showed. Things are changing as technology is changing. And what we see, what we believed and what we know is that there is a lot of gas in this disk, and star formation takes place. And this whole galaxy rotates about the galactic center. So the diameter is 100,000 to 180,000 light years. And the thickness of the disk is about 2 light years about, right? So that it's a thin disk, but still it is 2,000 light years across. So the light going from one end to the other it will take 2,000 years, but it is 1,000 times, right? So the length is 1,000 times. This is 1 unit to 1,000 units. So still it is thin, and our sun is about 28,000 light years from the center of it, and the whole system rotates, and the rotation is not like a perfect disk. The central stars go faster around the galactic center, and as you go further and further out, they go slower and slower, right? In fact, that's what we thought till we plotted certain radial velocity curves, which Tim had spoken in the previous one. And what we are seeing is it's not actually happening that way. What we are observing is the rotational curve decreases till a certain point and then it flattens out, indicating that there is dark matter halo around the galaxy. So much beyond the extent of the visible extent of our galaxy, there's another big halo of matter which is non-radiating, which does not interact with electromagnetic spectrum. You can't detect it in optical, infrared, radio, or another thing, but it shows gravitationally its presence, right? So what is this matter? We don't know. It's an important question, and people are studying it. There's another school of astronomers which believe that there is nothing called dark matter, and the rotational curve and the dynamical aspect of this should be corrected by using better models of gravity. Okay, so we'll not get into the debate. What we understand today is our galaxy, Milky Way galaxy, is a barred spiral galaxy, and this is what it looks like face on. So this is obviously not a photograph. It is an artist's impression, because nobody has ever gone far enough to image our galaxy this way, right? So these are constructed from theoretical models of studying velocity of stars and looking at other objects which probably look at us, which probably look like us, our galaxy. Okay, and these are done by studying the dynamics. So the structure of a galaxy, remember, is a property of the velocity of stars in it. So once Hubble and Emerson established that the galaxies come in their variety of galaxies, they started looking at all these nebulous objects, and they saw that the galaxies come in a variety of shapes and colors. You can see that they look like ellipses, they look like filamentary structures like these, cigar-shaped ones. They have spiral arms with bars in it. There's another one with a bar and a spiral, and so on and so forth. So we are looking at two. This is one galaxy which looks very much elliptical, and here which looks spiral. So the morphology of a galaxy, when we are talking of a morphology, we mean what is the shape of a galaxy. And the shape of the galaxy depends on various things which we shall see. It depends on the position angle from which we are seeing. One thing is they have different shapes. Some are spherical, some can be ellipsoidal. And if it's an ellipsoidal one, whether you are seeing it from here or here, right? So if I have something like, say, a watermelon, major axis and minor axis, it will look like a ellipse. But if you turn it around and see from this side, probably you will see it like a circular one, right? So if you're seeing a circular one, it may be a circular one, or it may be elongated along your longer your line of sight, right? Similarly, your spiral galaxy, if you see, you have a object of this kind, and you see it edge on, you will see it as just as a small rectangular thing, and you are seeing it at different angles. You see it's rectangular of different length to breadth ratios, right? So it is how you are seeing it, and we have no choice to see it from some other angle, because we cannot travel those distances to go to another vantage point and see. Our technology as of now is not good enough to do that. Right. So, but we can see many galaxies in different, from different position angles and different, right. So once you have that, there were various schemes to classify them. The most basic one, which was given by Hubble again, is called the Hubble tuning fork diagram, where he arranged all the galaxies. He said all galaxies can be broken up into three bins: the elliptical galaxies, the spiral galaxies, and spiral with bars. Sorry, uh, elliptical galaxies, spiral galaxies, and lenticular galaxies. Spiral galaxies, he broke them into two categories: normal spirals and barred spirals, right? So three basic ones: ellipticals going from E0, E1, E2 to E7. Yeah, so if it is circular looking thing, then it is E0. If it's slightly flattened, then it is E1, E2 to E7. And then a disk appears. You have the central big bulge and a very thin disk, featureless disk. These are the lenticulars. And then you have the other set where the bulge becomes smaller and the disk becomes more pronounced, and the disk has spiral features. So these are the spirals. And further, if you have a bar in that, then there are barred spirals and unbarred, and the normal spirals. There were some irregular galaxies which did not fall in any of these three bins. So Hubble said that these were odd galaxies. Probably there was not sufficient material there to form it into a proper structure. And these are peculiarities, and he brushed it under the carpet. At the same time, when Hubble lived, there were people who were interested in looking at these irregular or peculiar galaxies, but they were denied observational time to do that because it interfered with Hubble's works, and Hubble was a very powerful man at the time. Today we realize that these irregular galaxies or dwarf galaxies, they are very interesting objects, and there are innumerable such objects which were not observable earlier for two reasons. One, the technology was not good enough to see these fainter, smaller objects. And secondly, people were not allowed by some people whose works it could have created problem to observe, right? So Hubble, though, was a brilliant man, did a lot of work, but he also tried to monopolize astronomy in certain period of, right? So the same picture which we see on top is with actual images of today, better images. And in fact, it's looking slightly rounder, and we'll come to this later. Okay. Before we proceed a little ahead, we'll see that what happens is our Milky Way galaxy belongs to another cluster of galaxies, and this is called the local group of galaxies. And there are about 80 galaxies in that, right? Just a year back, if you had Google searched, it was 54. And today morning when I searched, it said 80 galaxies. So this number keeps changing. It will change because observations are increasing. There are better techniques of observing, better image processing techniques to refine. Sometimes you get a photographic plate and you don't see anything there. But if you do some good images processing, then you can remove the noise in the background and you can see these very faint objects around, right? So the numbers keep increasing, and they would as time progresses. So our Milky Way galaxy belongs to a local group where you have two major galaxies. One is Andromeda galaxy, which is larger than our Milky Way, two times Milky Way and our galaxy. Andromeda has its set of many satellite galaxies, and our Milky Way has set of other uh, set of dwarf galaxies. So it's kind of a dumbbell-shaped structure, and these dwarf galaxies obviously are interacting with these Andromeda and Milky Way. And in fact, Andromeda and Milky Way also are on a collisional path. And 3 billion years from now, they are going to collide, coalesce, and become one. Going back to the times, yeah. So and then these local groups, there are many such local groups which join together to form larger clusters of galaxies. These are two photographs of two nearby clusters. One is called the Coma Cluster, and the other one is the Virgo Cluster, right? So Coma Cluster has over 1,000 identified galaxies, and mostly they are elliptical galaxies. And SO stands for lenticulars. What I said, lenticulars are SO galaxies, and they have a few spiral galaxies there, and mostly in the outskirts. So it is an interesting thing to study the morphology of galaxies and see whether in dense region you find more ellipticals or do you find more spirals and so on. And we are trying to understand how are they formed, how do they evolve, and why do they change their shapes and so on. So yeah, so looking at these, and Virgo is a richer cluster. It has up to 2,000 probably galaxies, and it's a very heterogeneous mixture of spirals and ellipticals. Okay, and then these large clusters, further there is Fornax cluster and so on, and these many clusters, they join together to form the whole large structure of the universe. The universe is made up of trillions of galaxies. In each one you have billions, 100 billion stars. So there's a tremendous amount of stars in the universe. And you see a lot of activity which is going on in these galaxies. I wonder whether this animation would work. If it, yeah, so there's an animation here which would animate something which is on top here. Yeah, this is an actual picture, and what do you see here? There are some. It looks as though gas is flowing out from the galaxy, right? There are these streams. So what is happening is this galaxy is falling into the center of the cluster, and as it is going in, because of ramp pressure, the term you must have heard even yesterday, because of ramp pressure, the cold gas is pulled out from it, right? So this leads to, yeah, and the same thing you can see here. These are the outflows coming from galaxies, right? See, you see all these pictures of outflows, right? So all kinds of phenomena happens when galaxies get stripped of the cold gas. Then the star formation can get reduced, or when two galaxies collide, gas can get compressed and star formation can be enhanced, right? And obviously, when two galaxies come close and they merge, they'll change each other's shape and the galaxy gets transformed. So for a long time, people thought that the Milky Way was the only galaxy. Then when they realized that there are many more galaxies, they thought that these galaxies are separated by large distances and they have nothing to do each other. So the concept of island universe theory came up, where galaxies were seen as island universes, as unevolving and unchanging objects. But today, as we understand, we know that these galaxies are constantly merging, interacting, and transforming the shapes. And so these environment processes, they create a lot of havoc. You see these two galaxies in process of collision, and it's forming a ring galaxy here. You see a galaxy here which has a long trail here. here you see two galaxies merging, and these kind of antennas are being formed, right? And how does this happen? This itself was an enigma for a long time, till the time people, there was some very innovative, very um, creative people like Zwicky, and they said that it's galaxy which is causing the galaxies to transform. They create these tails and bridges between them, and they tried to attribute it to magnetic fields and various things. But finally, today we realize that it's the gravity which is acting at very large distances, at very large scale, which pulls stars out. When two galaxies come close and go past, there's a stream of stars which can be pulled from one to the other, forming a bridge between them, or because of tidal interaction, these are formed. So we'll see a few simulations which will show that. Here is NGC 4676, 4677. These are two ones. They also called the mice because they look like two mice. You know, there's one with a tail here, and there is another one which like two mice head-on colliding, and they are basically two spiral galaxies, which are. This is the stage which we are looking at, right? And if you leave them for another billion years or so, they will finally merge to become big one elliptical galaxy, right? So these n-body simulations were first done by Homburg, and they were very primitive ones, but the more meaningful and good ones came sometimes in 1970s and so on, by a brother and brother pair, Alan Toumre and Julie Toumre, and they simulated galaxies and showed how these big tails and bridges are created. And at that time, people thought that it was Hubble tuning fork diagram is a morphological scheme, right? You have ellipticals, and you have circular with more and more ellipticals, lenticulars, and you have spirals. So people thought that galaxies are formed spherical, and because of rotation, they become ellipsoidal. And further, if the rotation is fast, the disk appears, and that leads to formation of lenticulars. And then the disk, as it becomes larger, these spiral arms are created because of perturbations and so on, and spirals are created. So people thought that these are elliptical galaxies which are being transformed to spirals. While Toumre and Toumre, they showed two spiral galaxies merging to form an elliptical galaxy, and it totally reversed the whole process. And people did not accept them, and this was in 1970s, right? Just a few hundred years, and now you see these beautiful simulations where there's gas involved in it, dark matter, halo, everything, and these are run on computers. You basically write equations of motion for these n-body systems, and you solve them numerically, because for a system with more than two bodies, if you have an n-body system with three, you cannot find a general solution. So you have to, and here we are talking about billions of particles. So you have to do computational things to it, right? So these are gives a lot of insight into how structures are formed. And this is an image. If you could see the previous simulation, and you would have, maybe there's too much light, but you will see that the final product looked like an elliptical galaxy, and there were some kind of shells which are seen even here. So this is an indication of, this is a large elliptical galaxy. And if you see that in many different wave bands and put them together, you see that this is made up of many more galaxies. So many galaxies have merged to form this huge elliptical galaxy, right? And in many of these clusters which we see, we have giant ellipticals sitting there, which are cannibalizing small ones, eating the small ones and becoming bigger and bigger, right? So the term cannibalism is also being used. So now when you look at, so we said our Milky Way galaxy has, it has bulge, disk, and a halo. The disk component, as we realize, is the important thing, which finally tells you disk and the bulge, right? These are two very key things. If the bulge is prominent and the disk is very diffused or so, then you see it more or less as a elliptical galaxy, right? The bulge, the central bulge is big and the disk is thin, right? Not formed or disturbed, or the gas has been, then you see it as an elliptical. But if the bulge is small, compact, and you have a disk, then you see it as a spiral galaxy, right? So it's important to look at the structure of the bulge, and bulge, we classify them mostly in two types of bulges, the classical bulges and the pseudo bulges. So these classical bulges are formed from major mergers, right? And the pseudo bulges are the bulges which have formed over secular evolution, over a long period of time. If a galaxy is left undisturbed, then it settles down as a pseudo bulge. Apart from that, there are all kinds of other types like boxy bulges. It looks like a box, or it looks like a peanut, right? And very often, if it's a peanut, then there are two cores there. It's a merger remnant. Even boxy ones indicate some kind of a merger remnant, right? So these boxy peanut are also pseudo bulges. So basically, you have classical and pseudo, and we would like to look at them. So if you look at it, these classical bulges are spheroidals, which is hard to see at low inclinations. They are usually featureless. You don't see any spiral arms, rings, bars, or anything. And they are mostly made up of old stars. You don't see much of dust there or star-forming regions. And they are kinematically hot. By kinematically hot, what we mean is the stars are a lot in motion. They're all in all kinds of, there's a lot of velocity dispersion, right? It's not that they have attained one kind of a stable kind of a system. Pseudo bulges, they are flatter. They may contain substructures like nuclear bars, spiral arms, or rings, and they usually show signs of dust obscurations, younger stellar populations, and ongoing star formation. And they are kinematically cold, right? So that is, they are basically supported by the velocity of rotation of these stars, right? So another important thing and interesting, which has been established without doubt, is all major galaxies have a black hole at the center, and the mass of the black hole defines the size of the bulge. The larger the black hole at the center, the more massive the black hole at the center, the bulge seems to be larger, right? So there's a direct correlation between the mass of the central bulge and the mass of the black hole, right? There is a direct correlation. So bigger the black hole, bigger is the bulge. Basically, it's this black hole which is holding the whole galaxy together, right? And so the larger it is, matter falls in equally throughout, and it's holding it. So there are a lot of random velocities of stars. While if it is small, then slowly what happens is the gas settles in the disk and it starts rotating about the disk, and star formation starts taking place, and the disk becomes more obvious and easily seen from large distances, because essentially it's the young stars are the hot stars, and hot stars are bright stars, and hence you can see only the disk. You will not see the bulge and other features, right? So there is a relationship between the black hole and the central bulge. Okay, so we classify galaxy morphology by there are certain techniques. One is by doing photometry, right? Photometry is you collect the light of the galaxy and you see how is the light distributed, right? So you can draw probably contours. If you look at all galaxies, most galaxies, you'll see that they are brighter at the center, and as you go out, they look fainter and fainter. Okay, so if you do isophores, if you draw, that is those curves which connects regions with similar light intensity, you will see that you get these contour plots, right? So you can do this kind of so basically you can measure, or you can measure how much light is coming from the center, and you keep going out radially and keep studying how is it falling, right? So various mathematical models have been created, and there are certain mathematical functions which show how the light falls in an elliptical galaxy or in an exponential disk, in a disk galaxy, and so on. So we'll come to those expressions further. So our classification of galaxies into different morphological type is dependent on our visual impression of the images. So understanding the distribution of light is crucial for understanding the physics. The determination of brightness in an image is called photometry, where you measure light, but this process also covers determination of shapes and brightness profiles. Okay, so you can fix up various components to make one whole galaxy. Like you have the multiple component one, you have one component as a spherical object to give the bulge. Then you give a bar feature. Then you have a disk, right? So a disk, bulge, bar, and the central nucleus region, and you can construct these galaxies of this kind, right? So you have multiple, and you can study the morphological properties of these different galaxies of ellipticals, of spirals, and so on. And roughly, elliptical galaxies, they look simple. They are roughly roundish or ellipsoidal. The light distribution is pretty smooth, and there are no obvious regions where star formation is taking place, and there's no obvious dust lanes and so on, right? But there are many elliptical galaxies where we can get dust and other things, and that we shall see how we do it using certain software like Galfit and a little bit of image processing. Right, so they appear very simple, round, this, that, but really speaking, they are not so simple. And a detailed studies show that they range in shapes, their oblateness can be different, they can be triaxial, right? That is, you are making an ellipsoidal model, major axis and minor axis, and the other axis is same as the minor. So two axes are same. So one cross section will give you a circle, while the other one will give you the maximum to minimum. But there are certain which are triaxial. There can be three different directions where, right? So they are irregular kind of a thing. And this triaxiality probably, or it does indicate some kind of a disturbed system, some kind of a merger remnant, where it has not settled down into a perfectly spherical or ellipsoidal, right? So they come in variety of shapes. In fact, you can see dust lanes also in it. They range from the luminosity, how luminosity one type of ellipticals from another, there can be a variation. And some are supported by rotation, by the velocity of stars, and some are supported by the pressure within the temperature of stars and so on. And they can have cuspi and chord centers. Okay. So here, viewing angle also determines, like I already said, from which angle are we looking at an object makes a difference. They can look like spirals, or they can look like edge-ons, right? So how do we see, and what kind of obscuration there is, what kind of dust extinction there is, and various things which are required. And we can do that. And here's an example of one galaxy where inclination to the sky plane is 90 degrees. You are seeing edge on, and where the other one, which is 0 degrees, where you are looking at it face on. Yeah, obviously these are two different objects. We cannot have two images of the same galaxy from two different positions. Yeah, we are not yet technologically advanced. So how do we quantify galaxy morphology? We use something called the surface brightness. So surface brightness, I denoted by I, is the amount of light contained in a certain region of area. So you look at galaxy, you take a point in the galaxy, and in a certain area, we see how much of luminosity, how much of light is being emitted from that. Okay, so you take, say, suppose you have a D region, yeah, take a square region of D by D, and the distance from which you see, suppose a small d. So that will show you, that will give you alpha. Yeah, D, capital D is the size of the square, length, breadth. I'm taking a square in the galaxy of size DD, right? A square. And I'm seeing it from a distance D. So it subtends an angle alpha, right? Okay. And the flux which you are getting, it's the luminosity which you are getting from that area, is this L divided by 4 pi d square. D is the distance square. And so the surface brightness is given by this F divided by alpha square. So the surface brightness, as you should realize, is independent of distance of the object from us. Because as you go further and further, the light intensity falls by 1 by d square, but this angle also increases by d square, right? So hence it becomes the same, it's surface brightness. And so it is independent of brightness, but if you go very, very far, then you have to take into the cosmological dimming, yeah, the cosmological redshift and other things, which we shall not get into now, expansion of the universe which fits in, right? The redshift which comes because of that. That aspect becomes important, right? So, and the magnitude is given in arc seconds by this formula. This mu is minus 2.5 log I, and you have the constant. Hence the luminosity is given by 10 to the power of minus 0.4 mu b minus 27, luminosity of the sun, pc square. Okay. Surface photometry for extended objects such as galaxies, you do the surface photometry, and you are interested in studying how the intensity falls or how the ellipticity changes, and how is it dependent on the radius, right? So how is the intensity changing as the R is changing? At the center, your intensity is high. As you go out, it becomes lower and lower as a function of R. And also the ellipticity, how the ellipticity is changing as you are going from within to R, right? So it can either depend on the radius. Yeah, you have brighter at the center and fainter outside. And there should be a dependence on the morphological types also, right? Whether you are doing it for an elliptical or a spiral or a lenticular and so on, what kind of bulge it has and so on. Okay, so surface photometry is used when the magnitude of individual stars cannot be measured, right? Like in case of a galaxy, you get a fuzzy light. You can't individually measure the brightness of stars. In clusters, you can do that. When you are studying star clusters or even globular clusters, Some globulars which are very far, it could probably become difficult, but still individual photometry can be done. But galaxy, what happens, these are objects are extremely far, so you cannot individually measure light coming from one star is so much, one star is so much. So that's why you do the surface photometry, right? So even with HST, we cannot do that because distances are enormous. In the other one is a galaxy, the other one is a globular cluster, right? So this is an example of a crowded stellar field. Okay. So the basic concepts, roughly photometry itself is an art by itself, and there are certain software which are available. One software which was used tremendously earlier is IRAF, Image Reduction and Analysis Facility, but slowly it is being phased out. But by far it was a very comprehensive, a very good package to do analysis for astronomy data. Nowadays, people are shifting towards the Python, and AstroPy has various routines which can be used in place of IRAP, right? So one is the point spread function. One important thing we have to realize is the PSF, the point spread function. Even if there is a point object, as the light of this point object comes through our atmosphere, because of the turbulence of the place, it gets scattered. So however good your telescope may be, however good your optics may be, you will not get a point object as a point object. You get a smear, right? It's called an Aries Disk. So you use the point spread function, right? And you convolve it with the image. And so if the actual object looks like this, with this, when you convolve it, you get, this is what it is. So our atmosphere is doing this for us and creating fuzziness. Okay. So you can use this point spread PSF and reverse this, and from images which you get, you can reconstruct sharper and better images. Okay. Second important thing which is done in photometry is background subtraction. So you are trying to measure a particular star or a galaxy, but even from the sky around it, regions around it, there is some light which comes in. The background is also illuminated. It may be less illuminated as that object is, but it is contributing it to it, right? So when I'm trying to look at this mic, I'm also getting light from this. So if I can measure light from here, and that light is coming, which is in front too. So if I subtract this background from this, then I'll get a sharper image. So there are various techniques of doing photometry well, which we shall not do now, but like flat fielding and background subtraction and other things where you can enhance the quality of images. So here we have this radial light profile. If you see from the center of a galaxy and measure the brightness, yeah, you plot it, you will see that close to the center you have a high value, and as you go further it falls, right? So there is this Cirsic profile which gives you how the light falls, and this R indicates at what radius you are measuring, right? So at each radius you plug in the values and you'll find out what it is. So here you have some free parameters. Your N is called the Cirsic index. Yeah, just keep that in mind. And N equal to 1 essentially describes an disk, right? As an exponential disk. In an exponential disk, the light falls by this law, which you have here, where N should be 1. Okay. And for N equal to 4, we get something called the devacular law. And ellipticals appear to follow the devacular law. This N equal to 4. Okay. The RE here indicates the effective radius, that is the region within which half light of the galaxy is found, right? So you measure, you surface photometry, you get the brightness of the whole galaxy, and the radius within which half light, through which half of it is coming, is called the half light radius, which is RE, effective radius, and IE is also the intensity within this half light radius. Okay, so we have this. So yeah, so we have isophotos that you can do this isophotal analysis and so on, and you can get yeah. So when you look at these contours, if they are, it's an undisturbed galaxy, then elliptical galaxy, then you will see very perfectly sit one contour sitting another into elliptical patterns. But if it is a disturbed one, then you see this kind of a twisting or disturbance, right? There's, you can see some deformations here, you see certain things, right? So this is an example of some kind of a disturbed galaxy. So we can look at, there are different profiles which suit ellipticals, the same function which we have here, for different values of n, you get different profiles which show how the light falls. And you have ellipse fitting. Again, IRAF does it very well. And you can fit ellipses and see how the galaxies are. If these contours, these ellipses which show the distortion of light and diffusion, then you can see that the galaxies are disturbed ones. So you can break a galaxy into different components. You have the disk, you have the spheroid, you have, yeah, so two bulge, two component ones or three component ones and so on. And I'm rushing through this because when we are doing GalFit, you will see that better. And here you see the different profiles. The bulge goes by this dashed line, and disk follows this line, right? So bulge and disk are given by, the disk is given by this ratio, and the bulge is given by this function, yeah, where you have 1 by r by 4, yeah, like. So if you plot the stars in an object in a galaxy, this is what you are getting, and these are the three components which you have. You have the disk, you have the bulge, and the okay. Important ones are these scaling relationship. One is the Tully-Fisher relationship, which it is used to give you some kind of a hold on the mass of a galaxy. If you want to find out the mass, there is a mass-luminosity relationship. And for elliptical galaxies, they see you have a Tully-Fisher which says L is proportional to V squared max. So the stars which have maximum velocities, the squares of that are related to the luminosity of it. And the luminosity will give you what the mass of the galaxy is. Okay. While for ellipticals, you have something called, you take the velocity dispersion, and again L goes by velocity dispersion to the power of 4. Okay. And you get this relation between luminosity and radius, or mass luminosity relation goes by 1 by L4. Okay. So one is used for spiral galaxies, the other one is used for elliptical galaxies to get estimates of masses of these galaxies. And putting these, yeah. So we have this Faber-Jackson relationship where you have L luminosity and sigma is their velocity dispersion, right? Velocity dispersion. And you have the Coromandi relationship, which gives you the relationship between the luminosity and the effective radius. Okay. And putting both of these together, we get some kind of a, right? So once you have velocity dispersion, you have the effective radius and the luminosity of that, you get a relationship which is called this fundamental plane. And this will tell you how as you go from the center, your effective radius, you go from center to outwards, how does your sigma vary? Okay, so you have something called the fundamental plane, which is the relationship between luminosity, surface brightness, and the velocity dispersion. So what we can do as in the project is one is GalFit. GalFit is a software which is freely distributed, and it can run only on Mac or in Linux. You don't have it running in Windows, and it's very easy to use. You can run it. We'll have a demo in that to show what you do. You have an image of a galaxy, and you have an input file in which you specify what kind of parameters you're using, what is the major minor axis ratios, and what is the inclination angle, and you construct a model image. So what you see here is the actual image which you have, and we construct a mathematical model. By looking at it, we feel it's a circular one. So my major and minor axes are same. There's no inclination in it, and I make a mathematical model. This GalFit makes me this model, right? And when I subtract these two and I don't get a residue, then it indicates that my model is pretty good. This is what the actual galaxy is. But in some cases, I look at it and I see this is the major axis, this is the minor axis. I feed it in the input file and run it through GalFit on this image, and it has constructed this. I say you construct it at this angle, this thing, the galaxy of this size, which should be elliptical, and with one component or two components, so on. And you subtract the two, and you see here, right? By visual inspection, you see it looks like an elliptical galaxy, but the residue is showing that it's an a spiral galaxy. You are seeing some features in it. And similarly here you may say, okay, it's a spiral galaxy. I make a disk galaxy with a central core and so on. And when I subtract it, I'm seeing a bar feature also, right? So this is the mathematical model. This is the actual image, and this is the residue. And the residue, if it is empty, that means your model is perfect. But if your residue gives something out, then you see the features in it. So you can see dust lanes, other features, and so on. Similarly, you have a galaxy. This is the model. You subtract it, and you see features here. And you also see that the central object, there is some interesting, not a normal kind of a core which that kind of a galaxy should have, but it has a more pronounced one. So using these, we can fit, and the GalFit results show you what is the bulge of the galaxy. It gives you measurement of the total light of the galaxy, and it gives you measurement of the Sersic index. And using that, you can plot the Cormandy diagram and so on. And from that, specifically, ellipticals falls particularly specifically in a certain region, and lenticulars occupy certain space in this Cormandy diagram. And by putting them in these Cormandy diagrams, which I should show you here, you can find out whether the objects which you see are how many are ellipticals, how many are lenticulars, and these objects which you see, these are spiral galaxies, right? So this data was taken from Coma Cluster, from the central region of the Coma Cluster, and for 200 and odd galaxies, my student Nagamani, she did GalFitting for all these, initially with a single Sersic, then with double Sersic, multiple Sersic, and she got what classified them from on the basis of visual classification, then GalFit classification, found out the bulge to total light radius, and found relationship between of these and saw what is happening in and why are they more elliptical at the center and why and so on, right? So GALFIT is a very good technique to look at the structure of morphology of galaxies, and you get all these relations from which you can plot from the output of GALFIT, which you can plot, analyze, and understand what these galaxies are. And from the Searsic index, we can even specify whether these are classical bulges or pseudo bulges. And classical bulges are the ones which are formed from merger remnants, while pseudo are the secular evolution ones. So you get to understand what is the dynamical history of the whole system and so on. So this is one way of doing it. The other set we can do is by using simulations. I shall not touch upon that now, but you can do n-body simulations, and there are very powerful codes called, one is Gadget, and one of our students is working on that, where you can make models of galaxy. Again, galaxy is made up of the central region, the disk and bulge, and then you simulate them. You make smaller ones. You can adjust amount of gas in it, and you have. So this girl Sweta, she's studying major galaxies merging with small ones, and what happens to the disk if it is gas rich or gas thin, and how does the disk thicken? The disk changes its thickness. Does it change or not, or what happens and so on. So that's another aspect. And during this next 1.5 days left, we'll try to give you just a small glimpse of that too, so that later, if somebody is interested, can do projects with that too. So with this, I will end. Thank you. Are there any questions? Okay, so if you have a question?
There are two questions. Some students have sent to me. First one is, does supermassive black holes cause galaxy rotation?
Supermassive black holes, see, they are black hole setting at the center, and you can look at a simplified model where you have, say, the sun at the center and the planets going around it, right? So basically, why are the planets going around the sun? Is because of the gravitational pull of the sun. So the objects otherwise, if there was no gravitational pull and these had velocity, the planets, they would have traveled in a straight line. The very fact that they are going in an ellipse indicates that there is a force, right? Otherwise, they would have violated Newton's laws, right? So, and hence they're going. And since their velocities, the distances, mass, the gravitational pull is perfect, they are moving in those orbits. If they were faster at that location, they would have flown out and so on, right? In the same way, the galaxy is made up of stars and gas and dust, and everything is being held together by the gravitational pull of this matter which is sitting at the center. So at what radius is an object, a star is rotating, you have to consider how much matter is within the radius within it, and that will control its motion, right? So obviously the black hole does play a role, and at what distance you are. If you are close, the stars go very fast, right? And that's how they measure the mass of a, when they say that it's a 3 billion mass black hole sitting at the center of our Milky Way, it is from the rotations. They have mapped certain stars and looked at the velocities and at what distance they are from the center. They are circling a point which you cannot see because the black hole doesn't radiate or cannot be detected in electromagnetic radiation, but you see them going around a point. How far is the point? And using Kepler's laws, you can find out what should be the mass. So it's the black hole which is controlling the motion. The closer it is, it will have to go faster, and further it is, it will have to go further, comparatively lesser. There's this dark matter which is spoiling the fun. That's again messing with the motion. If the black hole itself rotates, which it can rotate, it surely will make an effect, but the effect will be felt more so close to it, but further and further down, the rotations of that black hole should not matter much. Like sun is rotating, and rotation of sun should make a difference to objects very close to it. But as you go further and further, it should play lesser and lesser role, right?
Thank you, sir. So there is one more question. How do stars move in a galaxy?
How do stars move? Yeah. So the stars, there are two, in our galaxy, there are two very simplistic descriptions. The stars in the disk, they are going around the galactic center. They are revolving almost in circular elliptical orbits, right? And the stars in the halo, they have all kinds of tumbling orbits, right? So the whole disk is rotating and they are all moving in the same way. And you have tumbling orbits all around, right? But now when they are looking at star velocities in a more refined way by Gaia and other satellites, where they are able to measure velocities of many more stars, they are seeing that very close to our solar, there are three clumps which are behaving in a different way. They have internal disturbance. This whole thing is moving, but there are internal kinematical differences. There are four lumps very close to the solar neighborhood. And these are because of the other effects of dwarf galaxies, which must have interacted with it, gone and fallen into our galaxy interaction, right? So it is not a very smooth motion.
Is there any probability of collision in there?
Yeah, so the chance of a star colliding with another star is very low. They can collide, but the probability is low. In the solar neighborhood, if you see the number of stars which are there in 1 PC square, the chance of two stars colliding is 10 to the power of minus 15. If you see the surface area of stars and the number of stars in 1 PC square, the chance, yeah, so stellar to star encounter is very low. But they can happen and they do happen. And more so it should happen near the center of the galaxy, right? And the distances between stars is enormous. For example, the closest star to our sun is 1.4 light years away, right? That light years away. Okay. So,
We have time. We have to vote.
time, madam, do you have time or no?
There was something, but
There's one more question. Is our galaxy in motion? If so, where is it heading?
Huh?
Is our galaxy
Yeah, yeah.
in motion? If so, where is it?
Yeah, our galaxy is rotating about the local group. See, I said our galaxy belongs to a cluster of 80 galaxies, which is called the local group. And this itself as a system is rotating about the local center of mass of this thing, right? And our galaxy is moving towards Milky Way galaxy. They are heading towards a collisional path, and they are going to collide after 3 billion years or so.
So there's one more. How are the planes of our solar system aligned with the planes of galaxies?
Our plane of
Planes of
there
solar
is
system.
there is a small inclination. I can check it up and I'll just Google search. There is a small inclination. It is not, you have the galactic plane. In fact, our sun at the moment is on the lower end of the galactic plane, but it doesn't remain there all the time. it moves up and goes down. So the stars are, the simplistic picture I gave was circular, but actually they go down and they come up, they go down. So presently the sun is below and it will rise up, but the disk is, there's a small inclination.
It says that the solar system moves the galaxy with 60-degree angle.
60, 60 degrees angle. Yeah, so there's a 60-degree angle with the galactic plane. Yeah.
There's one more. What do you mean by exponential disk?
Exponential disk is the disk where this light falls exponentially, right? Where the matter, so that basically describes how the matter falls, right? So that is, there's much more at the center and falls exponentially. Yeah.
So there's one more. Does sun move around galaxy?
Of course, it moves around the galactic center. Sun is rotating on its axis, and the equatorial plane of the sun revolves in 25 days. The top goes around 29 days. It's a differential rotation, and it goes around the galactic center. 22,000 years to complete one revolution around. So it must have gone around 5 times or so. It goes around the galactic center. Yeah. And it's traveling at almost 200 kilometers per second. The velocity of the sun around the galactic center is about 200 kilometers, 220 kilometers per second.
Which Kepler's law is used to measure the mass?
Pardon me?
Which Kepler's law is used to measure the mass?
This Kepler's second law. Second law, T square is proportional to R cube. First law is time period relationship. First one is they are going in elliptical orbits, right? So sun at one at the focus. Second one says that the time period of a revolution is square of the period is proportional to the cube of the average distance, say cube. And the third one is it sweeps equal areas in equal intervals of time. So it's the second law which is used. And obviously, when you go to black holes and other things, then you have to take in relativistic effects and other things. But mostly at large distances, even these Kepler's laws hold fine around even black holes and so on. Yeah, because they're not very close to these objects. Do we expect, there are some more, can you mention how shells form after galaxies collide? Yeah, so basically the shells are formed. There's the question from Yash Chaurasia. Essentially, it's the energy, exchange of energy. And as these two systems merge, the stars get totally churned up. Yeah? So what is happening is you have two disk galaxies which are coming in, which are rotating. And as they get inside, enter each other, they churn up each other, right? So some stars, they gain velocity and they get thrown out. Others, it's at the expense of others losing energy and they fall inside. So this happens in bursts, right? As some are gaining and some are. And that's why you see this kind of a shell structure. And finally, this will fall back and it will get smoothened out. There's one more by, do we expect bars to get stretched out of spirals due to different angular velocities at different radius? Yeah. So what happens is, see, the interesting thing is, earlier people thought ellipticals lead to lenticular spirals. Then we realized that the spirals which form can also form ellipticals. But I'm not saying that all ellipticals are formed as merger elements. Some are formed directly as ellipticals. And then there is an elliptical galaxy. At this moment, it may look elliptical where the whole gas and stars have been churned up. But after some time, the gas can resettle back and again it can start looking like a spiral galaxy. So ellipticals left over a period of time can again become spirals, and N-body simulations show that. And yeah, a barred spiral becomes over a period of time into a normal spiral, and normal spiral galaxies can form bars. So these bars and also are transient features. They are not permanent. We are looking at it at a particular epoch of time, and over millions and billions of years, this happens. Basically, these are stellar orbits, and due to perturbations, they keep altering. So do we expect, yeah, reason for supernova? Sasha says reason for supernova. Can supernova destroy a black hole? Supernova can destroy, see, black holes are extremely compact objects. There are two types of black holes which you have. One are the primordial black holes, which are supermassive black holes, yeah, which are believed to have been formed at the time of the creation, right after the Big Bang, after the first, right? These are huge million solar mass black hole. And there are other set which are the stellar mass black holes, which are formed by stellar evolution. So stars which are about 8 to 10 times more massive than the sun, they end up as neutron stars. And before they end as a neutron star, they blow up in a supernova, right? But if the mass of the star is, say, 20 times, 30 times solar masses, they don't end up as a neutron star, but they end up as a black hole, because neutron stars, still the nuclear degeneracy pressure is holding it up. But if they are more massive, then it continues to collapse to become a black hole. So black holes are extremely compact objects, and a supernova cannot destroy it, right? So they cannot destroy a black hole. Yeah. And there was a question, how are supernova formed? They are formed, supernovae are formed when massive stars, more than 8 solar mass stars evolve, and they go from stage of burning hydrogen to helium, helium to carbon, so on, till the time they have furnished iron at the center. Then they blow up as supernova. Random thought, just can we think of ellipticals as high entropy and spirals with well-defined structures as low entropy? If yes, wouldn't the conversation of ellipticals to spirals violate the entropy law? Yeah, so in one way, you are right that ellipticals can be thought of. See, the ellipticals are formed because basically it's the bulge which is being dominated, and the stars are in all kinds of random motion. And as we have seen, your spirals are merging, churning it up, and while in spirals, the gas settles down, and they settle in the disk, and star formation starts taking, and there is these are waves, right? The spiral arms also keep changing. The patterns keep changing over time. So these are kind of density waves, and these compressions lead to formation of that. You can't say that there is less entropy in a spiral. Your whole dynamics is slightly different from that in ellipticals. Okay, so maybe we'll stop for now, and if there are questions, you can ask in the WhatsApp chat and other ones. Thank you.
Thank you, sir. I think there are many more questions, but let's take them sometime else.
Am I allowed to, or?
There are 2 more questions.
Okay, fine.
Can you take them now?
Yeah, sure.
Okay, sir. First question is there any magnetic property existing or not? If yes, then which type?
Magnetic property where? If you ask about whether there are magnetic fields in galaxies. Yeah, in galaxy there are magnetic fields. Even our galaxy has magnetic fields, but they are very low, and yeah, and they are being studied. There are people who study by polarization and so on. They study magnetic properties, right? So whenever you have charge and it is in motion, then you should expect magnetic fields to be there, right? So there are magnetic fields in stars. Sun has its magnetic field. Earth has a magnetic field. Some planets, they do have the magnetic fields. Some planets don't have, like planets where they don't have, if the core is totally solidified, there's no charge which is flowing, then you won't have a magnetic field in that, right? But Sun has a magnetic field which is pretty strong, right? Earth has a very strong magnetic field. And galaxies have magnetic fields because, and stars have magnetic fields. So that contributes to the magnetic field of the galaxy. So initially people thought the magnetic field is responsible for the for various activity which goes on. And the magnetic fields do play a role in star formation and various things, right?
Yeah. There is one more question. How spectroscopic data is collected for galaxies and stars?
Spectroscopic data. Okay. So what is spectra? Spectra essentially is light as it passes through a prism or scattered by a prism or so, it gets scattered, right? The light is made up of different components in it. And each component of light, blue light, red component, each one, it refracts by different amount. When it goes from one medium to another, the velocities are different. Okay. Similarly, the scattering is different for each wavelength. So in telescopes, you attach these spectrometers. Okay. And earlier they used to direct the starlight through a prism or a prism and take a spectra. If you were present in the previous lecture of Dr. Timothy Hamilton, he showed that now they have they have spectroscopy with fibers on it. So you have an image of the sky. Suppose there are 500 stars there. You have different tubes, optical tubes which are connected. Yeah, you exactly know where they are. You put these tubes and you can have a grid of this and you take spectroscopy. Right? So spectroscopy is done by having some special spectroscope design which are put on telescopes, and you focus your telescope to the object you want and do it. So for galaxies, you don't do it for individual locations and points. You do surface. You have to do slits. You take slits along and do spectroscopy of that. And with that, you can get red shifted or blue shifted, showing that the galaxy is rotating and what's the velocity, whether the whole galaxy is coming towards you or moving away, and also the spin of the galaxy, because one end would be blue shifted, one would be red shifted. So,
under what mechanism the galaxies are creating their own groups?
Under what conditions? It's basically gravity, which yes, at the Big Bang, everything was blown away, thrown away. Those galaxies which got thrown away in the same direction, after some time they lost these velocities and the gravitational force started dominating and they started clustering. So it's the gravity which puts them. So matter was scattered all over and they formed clumps, different clumps in different regions. Right?
Last. Is there any possibility for a planet or a star to come out of the galaxy due to the external results?
It is possible. It is, if our galaxy, which is going to go close to Andromeda galaxy after 3 billion years, and our sun's age is 4.5 billion years. So our sun would not have evolved to the red giant stage. So if human beings don't destroy themselves with the nuclear bombs we have created, then some kind of life would exist then. And then these processes are small. So when you have some other galaxy coming close, so the gravitational potential can pull out planets from it, right? So in fact, from globular clusters are made up of many stars. And there are some free-floating planets. These planets which were formed around stars in globulars, they have been pulled out by interactions. Yeah. So if gravity of some other object which is large enough, the gravitational force is large enough, then the sun, it goes menacingly close, then it can pull them out. It can happen. But the chances of that happening to our solar system is pretty low. Yeah, we don't see any big object coming close by.
Thank you so much, sir. Two questions in the chat.
What will happen in radial light profile if we take logarithm function instead of exponential function? Could we take cube of distance instead of square of surface, right? Yeah, you can study it, and you pretty often you write it in logarithmic scale and so on too. Just the profile would look different. Yeah, so it is possible to, you can. And can we take cube of distance instead of square and surface brightness? No, you can't take cube of distance because the area goes by r square, isn't it? We are looking at the surface of. So if I look at any, let it be sphere, let it be a spheroid, let it be anything, you are looking at a small patch of it, and it is two-dimensional. That's why you take square, r square, right? And secondly, yeah, so that's why you have to take, you can't take cube there, you have to take square. But can we take logarithmic functions? Yes, you can take, yeah, you can. So these are, you just look at how well the brightness is falling as radius is changing. And to get it into a very decent form, which we see here, you get these exponential functions. Yeah, you get this. Yeah, this is the one. That's why you get it in exponential. But yes, you can write it in logarithmic scale also, right? Only it won't look like that, but it will go flatter. Okay. Okay, fine. So let us stop with this. Thank you. Any announcements? 2:30, 1 or 2. So next session is at 2:30. So let's stop here. People online, please join after 1.5 hours, 2:30 Indian time, which is 1.5 hours, where we will have a talk by Professor Avinash Deshpande. Yeah. Okay. Bye-bye.